Hey everyone, in this video, I am going to go over epoxides. And so just before we kind of really dive into it, so an epoxide is basically just a cyclic three-member ether. And the kind of base functional group is right here. And so there's kind of different things that we can do with epoxides. We can form them and we can open them. Those are kind of the two main things. But with forming them, we can do two different ways of forming them. And so the first is through a halohydrin formation, and that is going to use a halogen like Br2 in a water solvent. And then we deprotonate the alcohol and kick off the leaving group. And that will be like this. So the first step is to form the halohydrin, and then the next step is to deprotonate the alcohol. And then that alkoxide will actually go in and attack the neighboring carbon and displace the bromine, and we will get an epoxide that looks like this. And so another way that we can use is we can use the MCPBA reagent, and that will basically just form the epoxide in one step. And we don't really need to worry about having two steps. So from a synthetic standpoint, we almost always want to use MCPBA because we can achieve in one step what it would take two steps with the halohydrin. So on a synthesis type question, be sure to use MCPBA because that will be the fastest route in almost every case scenario that I can think of. So just as kind of a little side note, I know that this really confuses people sometimes, kind of the different ways that you could draw an epoxide. So you can draw an epoxide where the carbon chain is in the plane of the paper, or you can draw it where the epoxide is in the plane of the paper. It doesn't really matter as long as you are consistent. Yeah, I think that a lot of times people will check their answer and not really realize that they're the exact same structure. So just kind of be comfortable with both ways of showing an epoxide. So here I have the mechanism for the MCPBA reaction. I'm not super duper sure if you'll be tested on this mechanism, but I just wanted to include it just in case. So it looks like this alkene here is going to attack this O of the peroxide. And the sigma bond right here will go in and attack the other carbon of the alkene. So we've seen this before with bridge species like bromonium bridges, stuff like that, where the electrophile gets attacked, but it at the same time will go in and kind of attack the nucleophile, forming a bridge. But in this case, we have kind of a lot more going on. And so to not leave this proton kind of outstranded, we use the pi electrons here to form a sigma bond to that H. And we use these sigma electrons right here to form a pi bond right here. So we end with a carboxylic acid functional group, and we also end with an epoxide. And so we can kind of get a little glimpse here of the next part, which is the stereospecificity of epoxide formation. So this reaction is stereospecific. It does kind of change the products based on the stereochemistry of the reactants. So in this case, we have this Z alkene. And when we react MCPBA, these two groups, I'll make that a little smaller. These two groups are syn. And so when we form that epoxide, they will stay on the same side. And so since this is a meso compound, we don't need to draw the enantiomer. And in this case, the methyl groups are trans. And so when we draw the epoxide, we want to make sure that we keep that same, relationship between the two. And so we would draw them trans. And we also would, in the cases where it's applicable, we would get a racemic mixture. But in this final case, if we try to look here, we don't really have an easy geometry of this alkene. And so we see that we would get a product like this and a product like this. Let me draw the legs a little better. And so we don't show any stereochemistry at that carbon right there because it's not a chiral center. And we're not really trying to show like a diastereomeric relationship. Um, since we don't have a chiral center there, we do not really show the stereochemistry. Yeah, so in this case, since this carbon right here is bonded to two of the same groups, it isn't really stereospecific, but just kind of keep that in mind. All right, so now moving on to opening of epoxides. This is kind of the more kind of content heavy aspect of epoxides because formation is super easy. But when we open epoxides, that's when we need to be a little bit more careful looking at the conditions and then predicting the products. So there's two ways that we can open epoxides. We can either open them under acidic or basic conditions. And I don't really exactly like the terms here, acidic and basic, because sometimes we'll just have a strong nucleophile open and it's not necessarily a strong base. So look at the nucleophilicity of the nucleophile, and that can kind of also lead you to decide whether it's going to be acidic or basic opening. So acidic, similar to an SN1 mechanism, we have a weak nucleophile like water or alcohol, and we need an acid catalyst. And this is because the nucleophile is not nucleophilic enough. And so adding the acid catalyst will make the epoxide ring more electrophilic. And so the nucleophile will attack the epoxide now that it's more electrophilic. And similar to an SN1, we attack, or similar to an SN1, we attack the more substituted side of the epoxide. And so again, the first step is the acid workup or the acid step. And we'll just assume a water solvent here. And so now the O of the epoxide has a positive charge. And so because it has a positive charge, it's going to try to pull electrons more than it normally does to try to regain neutrality. And that will basically make these legged carbons more electron deficient. And that is what makes the epoxide now more electrophilic. So now the electrons that were kind of guarding the legged carbons are now no longer there, making it so that even a weak nucleophile like water can attack. And so, like I said before, the water will attack at the more substituted position. And so we would get something like this. Just going to move this actually. So now we have this species, and then we would go ahead and use another water molecule to deprotonate and bring us back to neutral. And so I know that a lot of times people with the chiral centers, I didn't really draw the chirality here, but they get confused because they want to invert the stereochemistry from wedge to dash. And we will see this in a second. But if you go from something that's on a wedge being down, like in this case, I'll just go ahead and draw it in. So if we say that that's on a wedge, when the water comes in and attacks, it will push this group right here up. And that will actually invert the stereochemistry. So when we say invert the stereochemistry, it doesn't always mean from wedge to dash and dash to wedge. It just means, changing from R and S. So when this oxygen comes in, it pushes this methyl group up and that inverts it. So we go from wedge down to wedge up. We don't necessarily go from wedge down to dash up because that would be flipping twice basically. And then I'll go ahead and add it right there. So that was kind of the mechanism for opening under acidic conditions or a weak nucleophile conditions where we need an acid workup. But if we have a strong nucleophile, we don't need the acid catalyst because the nucleophile is nucleophilic enough to attack the epoxide ring. And like I said, this is with a strong nucleophile, so like hydroxide anion or an acetylide anion. And similar to an SN2, we attack at the less substituted side. So that is kind of the major difference. So actually, I'm going to fix this. So in this case, we would attack at the less substituted side. And so the methyl group right there will stay down and on a wedge. And so we don't change the stereochemistry at that chiral center because we don't do any chemistry there. But now we form an alkoxide anion, which we need to work up with an acid workup step. And we would get something like that for our final product. And so again, you can leave your answer like this, or if you really wanted to, you could rotate this molecule to get the methyl group in plane and put the OH on a wedge or dash depending. But I would not recommend this just because I feel like this introduces another area where you could just make an error. So I would just kind of get to this point and leave it and not risk those points. And so the mechanism here is we don't need a acid catalyst. So we just go ahead and have the nucleophile attack. And like I said before, it attacks at the less substituted side. And we want to conserve charge. We started with a negative. The negative should be on the oxygen. And then we go ahead with our acid workup step. And we would get that. So again, the mechanisms for these opening reactions are not super difficult, but knowing the difference between the two, knowing that strong nucleophiles open at the less substituted side, whereas weak nucleophiles require an acid catalyst and attack the more substituted side is very important. And then finally, yeah, the regioselectivity and the stereospecificity of these reactions. So just kind of another example where if we are opening under strong nucleophilic conditions, we have an SN2 and we would get this because the OH will attack at the less substituted side. And since we are not attacking the chiral center, we kind of just leave it alone. And then after our acid workup step, we end with this. And you can leave that the way it is. And then with the acidic, we first want to form the electrophile or the better electrophile. So we would get this, and that is just kind of like a transition state. And then we have HCl in aqueous conditions, which basically just means HCl in water. And so in this case, our nucleophile is going to be water. And we attack at the more substituted side, opening up the ring. And now we see that we push these groups that were down, we push them up because they were here and then the water comes in and pushes them up. But again, the phenol was on a wedge and it stays on a wedge. It just goes from wedge down to wedge up, which is going to invert it. And then the last step will be to deprotonate and arrive at neutrality. And so, just comparing the two, we can see how they're different. And then I just have, another additional problem. So if we have Br2 in light we will get the most stable radical intermediate. And then if we expose this to LBA, this will form the less substituted alkene. And so we would get something like that. And then if we use MCPBA, we would get an epoxide that looks like this. And we would get a racemic mixture. Just for space, I'm going to go ahead and do that. And then we have a sodium acetylide in DMSO. And then we have an HCl workup step. So this is indicative of a strong nucleophilic opening, a basic opening. So we'll attack at the less substituted side. And we will leave that chiral center alone. And then we have our workup step. So we end with this product right here. And then this is basically the same thing, but just changing the base that we use to form the alkene. So in this case, we have this alkene since we have a small base. And then when we use MCPBA, we have this. But again, note how there is no chirality shown at that chiral or that carbon right here, because we're bonded to two of the same groups, not a chiral center. We don't really need to show stereochemistry there. And then similar to before, we use sodium acetylide. And then we will open at the less substituted side, which would be here. And we move this group from down and on a wedge to up and on a wedge, and that will go ahead and invert our stereochemistry for us. So we're all good there. So those are just some examples. And then I have a tip for synthesis. So if you see that there's a kind of like two carbons and then an alcohol, I would think epoxides, because when you open up an epoxide, it puts kind of two carbons in between the site where the nucleophile attacks and the alcohol. So in this case, we have, if we look, we see that there's two carbons and then an alcohol right there. But we see this ether, maybe we use an epoxide to form that. But if we look at our starting product, it's going to be that, and there's no carbons in between. So we know that we didn't use an epoxide to form that. But we did use the BH3 reaction. And so that will be our product. I'm just going to not write the other steps just for simplicity's sake. And then we want to deprotonate the OH to form the alkoxide. So we can use something like NaH. And then if we expose that to an epoxide, I'll go ahead and actually separate this. So now we formed an epoxide. And then now if we go ahead and expose that to an epoxide, it will open it up. Okay, I just drew it going down instead of up. So after this, we can see the two carbon kind of intermediate, and then we work it up with an HCl aqueous condition, and we arrive at our product. So just kind of be wary about two carbon plus an alcohol, and I would think epoxide, maybe that's not the case, but just kind of, it should be raising red flags that it probably is. But hopefully that introduced the ideas of epoxides. But if you have any questions, feel free to ask. Good luck.